Alright, welcome back. So we're going to continue with our discussion of Chapter 5, moving on to the last section, Section 3, talking about force and motion in 2 dimensions. So far we've talked about how to resolve vectors so vectors aren't in the same direction, breaking them into components. We've talked about friction, and now we're going to put those two things together. So first let's review equilibrium, because this is going to become important when we talk about force and motion in 2 dimensions. So equilibrium occurs when the net force is 0. And if net force is 0, that means that there is no acceleration. Okay, because we know acceleration causes force. It still means that there can be forces acting on the object, but the overall force, or the net force, is 0. If there's no acceleration, that can mean one of two things. It either means that the object is moving at a constant velocity, so the same speed the whole time, which would still be no acceleration, or it is motionless, or basically just sitting there. Forces may be acting on it, but the object's not moving. And they're all adding up to 0. So remember, net force is 0. We would say the object is at equilibrium. And this is really important when if we know a force acting one direction, trying to figure out the force acting the other direction if the object's at equilibrium, that net force equals 0 can be helpful there. Okay, so what if we had 2 forces, but they did not add up to 0? Okay, well, there could be a third force that will cause the object to be in equilibrium. Think about it like tug of war, only now with 3 objects pulling on the object instead of 2 forces pulling on the object. So this third force that will put the object in equilibrium is said to be the equilibrant, which is the opposite of the resultant. Okay, and this is the force that puts the object in equilibrium. So what we do first is find that resultant, and then the equilibrant is opposite in direction of the resultant, but it's the same magnitude. So let's take a look at an example. Here's our object, whatever it is. Let's say we have one force acting this direction, and one force acting in this direction. Well, if we break each of these into their components, an x and a y, and the same thing for this one over here, and we add up all our x's and we add up all our y's and we do Pythagorean's theorem and we get the resultant, if they're both like this at an angle, then probably our resultant is going to be something like that, because that would be the 2 forces added together. So this means that our equilibrant then is going to be opposite in direction but equal in magnitude, and I'm kind of running out of room to draw out the same length, but this would be our equilibrant and this would be our resultant. Okay, and we'll do some examples with that. Okay, so the last thing we're going to look at with this section is motion along an inclined plane. So far we've looked at things that are only horizontal or only vertical, and now we're going to look at things at angles. Our free body diagrams are going to look different because not all the forces are just vertical or just horizontal, and we're actually going to tilt our free body diagram to make it look more normal. So let's say we have a skier going down a slope. Okay, so here's our slope, and it's going to make an angle. And so, remember, free body diagram, we're just going to draw a box, so that's our skier. We know that force due to gravity is always going to be vertical no matter what. That's not going to change. Okay, but everything else now is going to be at these angles, and that makes it really hard to solve for. Okay, our F sub n, or our normal force, is going to be perpendicular to the slope, because that's the surface of contact. So since this is the slope, that makes this our f of n. So again, that's already at an angle. It makes it more difficult to solve for. And we've also got force due to friction, which is opposing the skier's motion, and it's parallel to the hill because that's the direction the skiers travel. So we have force due to friction acting here, and we have the force of the skier in that direction, or really just gravity pulling him down, but that's the direction he's going. Okay, so we have all of these forces except for the force due to gravity at an angle. So it makes more sense to try to shift the free body diagram so that everything is either horizontal or vertical except for gravity. Then we only have one force that's not at an angle. Whoops. Okay, so to do that, well, we'll probably talk about it in the next slide, so let's do that. Okay, so what we're going to do is make the coordinate system normal, or we're going to move it so that the whole thing is sitting horizontally instead of at this weird angle. So now only the weight, or F sub g, is not directly on the coordinate system. It's the only one that's going to be at an angle. We're going to draw a picture of this in a second. So the magnitude of the normal force is no longer equal to the weight of the object when we're on an inclined plane. So if you remember from chapter 4, we talked about how the normal force and force due to gravity are equal and opposite. But now that we have this angle, that's not going to be true anymore. So we'll tip this free body diagram and we'll talk about how that works. Okay, we're going to break the weight up into its component vectors because the force due to gravity, or the weight, is the only one that's at an angle. So we'll get Fg of x and Fg of y, and then we need to find the angle. Okay, and that's using this difference between the x-axis real, which was the initial drawing, and the x-axis moved. And that's equal to the differences between the y-axes. So let's go back to our picture, and we'll do all of this. Okay, so the first thing that we're going to do, is take our angle, and we're going to make it horizontal. So that most of these forces are now going to be either horizontal or vertical. So we've taken this right here, and we've made it horizontal. So now that means that our normal force is now, again, still perpendicular to the surface of contact, but now it's directly straight up. And we've also got our force due to friction in this direction, and gravity, which is pulling the skier down. We'll just put him in right there. Okay, so now the tricky part comes in trying to figure out how to put in our force due to gravity. Well, this is where that angle comes in. So this is what we are going to call our x real, because currently that is the x direction. This one that we moved, that's our x moved. Okay, and as you can see, here's that angle between our x real and our x moved. Well, when we move our free body diagram, the difference between the x real and the x moved, or that angle, now becomes the difference between the y real and the y moved. Okay, so if I take this angle, and this is my f of g, if I tip it horizontal, now my force due to gravity is pointing out to the right. So I'm going to draw that in. And again, we will talk about this in class as well. Okay, so now this was originally my y real. Okay, and now I've moved it. And so now to put in my components, here's my Fg of y. Here is my Fg of x. Okay, this is my y moved because that was originally at the angle and I've moved it to be y. Here is my y real that is now here. And so this angle is equal to this angle. So the difference between my two x's is now equal to the difference between my two y's. And again, we'll do an example in class because I think that's the most difficult part of this. But if you can get that angle in the right spot, now you've got all of your components except for your f of g. That's the only one at the angle. And now we've got all of our other forces in either x or y directions. Okay, and so again, we'll do some examples of this in class. Okay, so we've got that difference between the x-axes equal to the difference in the y's. All right, have a good day.